Now, let's welcome Swakshar, the speaker of the fourth talk, Unsupervised Cardiac Video Translation via Motion Feature Guided Diffusion Model.
Good morning, everyone. First, let us start with a very common type of cardiac MRI video that is called cine-CMR imaging. As you can see that cine-CMR actually provide you excellent structure quality. And this structure quality actually useful for tasks such as disease diagnosis or cardiac resynchronization therapy, etc. But cine-CMR video does not provide you accurate tissue movement, and you need a lot of post-processing tasks to get those tissue movement out. However, there is a more advanced CMR technique that is called displacement encoded simulated echoes or dense CMR. As you can see, that dense CMR provides you accurate tissue movement because it's directly encode the motion information into the MRI process. But this information comes with a cost of lowering image quality. As you can see it from the magnitude images that has very bad quality of texture information. In this work, our goal is to synthesize good quality or cine-like CMR texture information from a low-quality dense CMR images. But this has its own challenges. The first one is that if you collect cine and dense CMR videos from a same subject, as you can see that cine and dense CMR have different spatial and temporal resolutions. And this is because cine and dense modality has different acquisition time and acquisition protocol. And current diffusion-based model actually require exact cine and dense pair that you don't have in practical situation because cine and dense form a spatio-temporal misalignments. This is a little background of video diffusion model. This is the overview of our method. In the first section, we have a pre-trained temporal registration network that extract motion information from cine-CMR images. Then we use this motion information to extract motion features and use these motion features to guide the diffusion model to synthesize cine-like CMRs. So first, I will start from our proposed latent temporal multi-head attention network. Similar to classical registration network, ours also architecture has an encoder-decoder architecture. But unlike classical registration model, we have a temporal attention head encoded directly in the velocity space that give you more expressive and scalable representation of the encoded velocity and can capture global temporal dependency of cardiac videos. And we use this loss function to optimize our registration network. Then we use this pre-trained registration network to extract motion features because cardiac motion oftentimes has a complex motion dynamics. So instead of directly providing this complex motion or displacement field as a condition to the diffusion process, we extract multi-level motion feature with our spatio-temporal motion extractor. And this spatio-temporal motion extractor has first has 3D convolution layer, then followed by a spatial and temporal attention head. And then we use this motion feature as a condition to guide the diffusion process to synthesize high-quality cine-like texture information. Interestingly, during the inference process, we don't actually need the registration network LTMA. So we replace the registration network with already provided displacement field from the dense CMR video, as dense CMR video provide us the displacement field. And we use those displacement field to synthesize texture information. And this is our dataset that you use, the Cine dense CMR dataset. In the quantitative evaluation, we use the FID and KID codes code to evaluate the image quality, and FPD and FID BID for video consistency loss. As you can see that our model can provide excellent image quality and better quality of videos. And this is an ablation study that shows the effectiveness of LTMA and motion feature STME module. In the visualization of our generative model, in the left side of the panel, as you can see that given the input dense images, our model can get a better visual structure and motion consistency. And in the right panel, we show some of the animation of our synthesized Cine-like CMR videos from given a dense, low quality, dense images. And the rightmost row basically show you the Cine reference that actually used as a reference to show how the texture quality actually should look like. Because this Cine reference collected from the same subject, so the texture should be look somewhat like Cine references. As you can see that our model can get the Cine references pretty accurately. Then we evaluate our model on the downstream segmentation task. We basically have a pre-trained standard Cine CMR unit, 3D unit, and then we test that pre-trained unit on dense CMR images, and we get the dice score actually degraded significantly when we test in the dense CMR images. But when you test on our synthesized CMR images, the dice score actually has better retain there. And those are some of the animation of the segmentation visualization from our model, and also from testing on directly dense CMR videos. In conclusion, we are the first to propose a diffusion model that allow us to synthesize really good quality structures from spatiotemporally misaligned videos like Cine and dense images. We also propose a latent temporal multi-head attention registration network to capture cardiac motion. And we propose a spatiotemporal motion encoder to encode motion features from the complex cardiac dynamics. Thank you, everyone. Thank you.